Hi, I'm Nat Pryce.
Hello, it's Duncan. Nat and I wrote a book together called Java to Kotlin, a refactoring guidebook, which is gratifyingly now translated into Korean. In the introduction to the book, Nat wrote about the grain of a language, how it differs between Java and Kotlin. This seems to have struck a chord with people, so we thought we'd pull on that thread today and have a look at the grain of Kotlin and how it's changed over the 5 years we've been using the language.
So metaphorically, and it's not our metaphor, we borrowed it from the C2 wiki, a programming language has a grain much like wood. So carpenters working with wood take the grain into account when choosing their tools and when working with the wood, cutting, planing, and so on. And if they do not work with the grain of the wood, then the work that they do is harder, and that the results that they produce are worse. And for programmers, it's much the same. So if we work with the grain of a language, what we find is that work is easier and we produce better systems faster. And by better systems, I mean more reliable, more performant, more easy to change. If we work against the grain, we add to our workload, we introduce risks, and we do so for an uncertain payoff. So a language's grain forms over time. Right? The designers who create a language, the designers of Kotlin, had an idea about what they thought would make a good program. And users learned how to use that programming language. They found edge cases, interesting interactions between features of the language, encoded that in their code, then shared that code as libraries with other people who built on it. And over time, some things in Kotlin became easier, and some things became more difficult to discourage certain what were seen as bad practices. Right? So there's a sort of a feedback loop over time, forming the grain of the language, and therefore affecting the way that we work and the results we produce. So the designers of Kotlin clearly had a grain in mind when they produced the first version. And that grain was clearly influenced by, but different from Java. Right? So they had to walk a tightrope between Java compatibility, because they were targeting the JVM, targeting Java programmers, right? But also addressing what were seen as the most challenging aspects of Java programming and the common programming style. So they address things like mutability, null safety, and many other aspects of Java, producing a style that was significantly different. Right? So Kotlin's grain seemed to guide one towards an immutable domain model and a functional core imperative shell architecture, which was quite different from what people were producing, say, with Spring Boot. For example, so on one side here is Spring, showing typical Java style of the time. A lot of annotations, reflection, automatic composition of your application by class path scanning, and as a result, the composition sometimes can only be checked at runtime, and we have to write maybe some code elements that are just there to assist the class path scanning and composition features of Spring, but don't actually do anything. And on the right, an example of HTTP for K, a program doing the same thing, but written with Kotlin style in mind, written natively for Kotlin, where the composition is static, type-checked. We're working with functions rather than classes. And we have more feedback at compile time than we do in the Spring example. So the existing grain of Java did influence Kotlin somewhat. So things like late init were added to the library, to the language, to allow use of things like Spring, where composition happens before your code runs, but you don't really want to care about the fact that these things could be null. By the time your code runs, that object is provided to you by Spring, and you don't want to worry about that in the type system, so late init was added as a compromise between type safety and convenience.
Not all of Kotlin's grains seem deliberate, though, at least not at first. We'll look at a few things that took us by surprise.
So one of the first things we found was that there was an interesting relationship between null safety and extension methods. Extension methods were initially promoted as a way of adding convenience methods to types that you don't own. But what we found was when we started, as Java programmers, getting used to using null again and using Kotlin's null safe operator, the null safety reference, (dot), gives preference to the receiver. If we want to call a function with a possibly nullable parameter, in Kotlin that's quite awkward. If we want to call an extension method on a potentially nullable reference, that's a lot more convenient. So we started changing our functions into extension functions just for the convenience of allowing them to be null. And then we realized that we could make those names shorter, and our code became more concise and expressive, and we started writing more things in extension functions, allowing us to use null more easily and more concise code in a feedback loop that surprised us and produced what we felt was much more concise and easy to understand code, and we started using extension functions by default rather than as just a special case for other people's types.
We can see another example of accidental grain, maybe lack of grain in error handling. Removing checked exceptions was against the grain to make things explicit. We now have to hunt to see what's going wrong, but it was with the functional grain of the language, because functional programmers hate exceptions. And the high-order functions, they're complicated by exceptions. What is the signature of a map taking a transform that can throw IO exception? Two young men discussed this at Kotlin Conf in Copenhagen. In that talk, these pups bemoaned the fact that Kotlin removed type-safe error handling provided by Java, and the problem is and was there was no canonical Kotlin way of doing error handling. There was no replacement for checked exceptions, and the Kotlin result type has not been widely adopted, so that error handling is compromised. JetBrains policy, as we see from APIs and libraries, seems to be just to throw exceptions and sometimes document that they're thrown. But documentation doesn't help the compiler tell us that a function could fail, and we should be prepared to do something about it.
So we kind of acknowledged that the checked exceptions ship had sailed, or sunk, but we and a number of other people, Arrow and other people, tried to fill the gap by using some types of sealed class hierarchies to model the fact that a function could either succeed or fail. Right? And then provide some useful operations that allow us to compose functions that can fail, fallible functions. So a flat map composes a result that I've received from a fallible function with another function that can fail, short-circuiting that evaluation if the previous function failed. Get and recover allow me to escape from a sequence of result or fallible functions, providing just a plain old value back to normal pure function land. And when we use these, we can compose functions that can fail and type check our error handling. However, once you start writing code like this, where you have a pipeline of fallible functions passing values through flat map, and you want later parts of the pipeline to be able to refer to values computed earlier in the pipeline, you end up with quite unreadable code with this deep nesting called the arrow anti-pattern, ironically. And that really made our code difficult to understand. So we wanted a solution we were looking for a solution to simplify logic where we had sequences of code, sequences of operations that were composed through these monadic binds. Flat map is a monadic bind. Result is a monad in functional programming terminology. We wanted a solution for that.
Ah, yes, monads. Nat showed some code very much like this at Kotlin Night in London. And I remember saying, Nat, you have to find a thing to call that isn't flat map. Flat map makes no sense.
Yeah. See, I felt that I was working with the grain of the language by calling it flat map, because flat map was the name that was used in the collection library, in the standard library, for basically doing monadic bind of collections. And collections are monads if you are thinking like a functional programmer.
It's taken me years to appreciate the correspondence between collections and monads, and so of course I now can't tell you. But I am now very used to flat map being used as a continuation for control flow. And I don't think I'm alone. Kotlin has shaped us at the same time as we have shaped it. But nevertheless, expressing control flow this way is not very friendly. It's logical, but it obscures the flow until you're used to it, and then it's hardly ideal.
Yeah. So other functional languages, Haskell, right, have special syntax for monadic bind to allow error handling or other imperative or effectful computations to be expressed in a pure functional language. And we were sort of thinking, this is something we would get in Kotlin, right, one day, right? So this is what we thought we might end up getting. This isn't real language. This is just us imagining. But this is syntactic sugar that desugars into that massive nested tree of flat maps. Scala has a similar kind of thing. We were thinking that it's so obviously difficult to do error handling in Kotlin. Surely we were going to get language extension to help us do it. But we didn't yet, right? So instead, we had to rely on the language features that we had. And what we had was inline functions. An inline function will allow you to pass a block to a function call. The block and the function call will get inlined into the call point where you're calling it from. What that means is if there's a return statement in that block, it will return from the calling function. So here's the same piece of code that was horribly nested, turned into a much easier to understand linear flow, where the on-failure inline function is being used to return the error case immediately that an error is detected and unwrap the result holder back to the success case if there isn't an error. Right? This greatly simplified our code, performed very well, worked in that way with the grain of the language, but did come at the expense of all of this boilerplate. Not terrible boilerplate, idiomatic, you could argue, but not ideal.
So when we started writing this talk, we thought that Kotlin was a language that favored expressions over statements. Expressions are the bit of the language that yield a value. Statements are the bits delimited by the semicolons that aren't there. So the whole of the when there is an expression. The things to the right of the equal signs are expressions, but the assignments themselves are statements. Far more of Kotlin is an expression than Java. But inline higher order functions, like on failure here, they mix those two concepts because we can have a return statement inside the Lambda expression. And this is what do notation effectively does. It converts flat map expressions into statements. In Kotlin's flow typing, the places where the compiler infers the type of a variable given previous statements is a statement-oriented feature. We'll come back to that a little later. It's all very well, but if you want to integrate two libraries that use different result types, you're in a world of pain. And the truth is that Kotlin libraries basically use exceptions. What can we learn about the grain of Kotlin from error handling? Maybe the aspect of the grain that error handling illustrates is conservatism. The language designers didn't have a good enough solution to the problem, so they waited until one could be found, and they still haven't found one, so we're still waiting. Thank you.
We're not alone. Okay. So, in working with the grain of the language, we had to experiment invent some things, find that happy medium, that compromise between the purity that we would like but didn't have, the realities of the JVM, the realities of our team, the people that we're working with. And we basically agreed on some signals, some things that would cause us to stop what we were doing when we were writing code and realize that we were sort of veering off outside the grain of the language into something that was introducing more risk or more work than we wanted. Right? And this is what we decided in our teams. Right? Other teams might have different preferences, but in general, we were trying to work with the grain of the language and be less Java-y and more Kotlin-y. And we were thinking that our experience, especially of error handling, would point Kotlin's evolution in a way. And we knew that we weren't the only people struggling with error handling, as a ripple of applause verifies. We would sort of it would push Kotlin in a Scala-like direction, right? In Haskell, that do notation, we showed our fictional example of, but in Haskell, a do notation is mapping to monadic binds. Monadic binds are defined by type classes, so that as a programmer, I can write my own types and then define how they can combine in a monadic way. And so we were thinking, well, if we're going to get do notation, we'll probably get type classes. Type classes will address some of the problems that we're having with extension methods, which is they're not dynamically dispatched, they're only statically dispatched. And we'll end up with a language which is like Scala the good parts that's easy for Java programmers to adopt and start using in practical work.
At the point that Kotlin was released, Java was taking 3 years between releases, and it was looking as if it was dead in the water. The JVM was a credible platform, but the industry was moving to new paradigms way faster than the Java language was. So why was Scala not the answer? Scala was an experimental language, a place for people to try out ideas for PhD theses. It was in principle a mixed OO language, mixed OOFP language, but in practice it was adopted by functional programming enthusiasts. Any replacement for Java had to be close enough to Java that the average Java developer could see how to get there. The center of mass of the Scala community and the Java community was just too far apart, I think. You can't get from canonical Java to canonical Scala. But you can get from standard Java to standard Kotlin, and we know because we wrote a book. Kotlin was and is the adjacent possible to Java. Nevertheless, or maybe because of this, though, Kotlin doesn't do some things that other functional languages do.
Yep.
Oh, I'll go then.
There we go.
We'll get there. Right. 2 clickers.
Concurrency. This is why I don't like coroutines.
So we weren't alone in our view that Kotlin would move towards Scala. This devastatingly handsome man pretended to give a talk at the first Kotlin conf in San Francisco about creating a build tool. But actually, it was a Trojan horse for Cedric to talk about ad-hoc polymorphism and type classes. Type classes allow programmers to add polymorphic operations to a type without changing the type declaration. So say we have a cat, and we want to sort a collection of cats. Now, this doesn't compile because cat doesn't implement comparable. Cats are incomparable. And we don't own the cat type because nobody really owns cats. So we can't make the cat implement comparable. So how do we sort? Now, the Java solution to this is a comparator. Effectively, we make a sorted with higher order function that takes as a parameter the way that we compare cats. Now, what if we could provide a way to magically find a comparator for a cat and then automatically have that used by our sorted function? This is ad-hoc polymorphism, and Cedric's talk goes on to talk about Keep 87, which was a Kotlin enhancement proposal to have the compiler do that for us. There was a special syntax. This is one of the special syntaxes proposed, this given. So the given tells the compiler that it should be looking for a conversion. And there was places for it to look for conversion, like extensions of companion objects of cat or comparator, for example, a sort of search path, if you like. Now, for several years, Keep 87 was refined, reproposed, and not adopted. We just didn't get Scala-like type classes.
So we didn't get type classes, we didn't get do notation, but we got other things. Right?
Coroutines. Coroutines came along after the initial release of the language and have had a major effect on the way that many people use it. Now, Kotlin inherited its original concurrency mechanism from the JVM. That was mostly fine for server-side work, where we rarely need coordination between threads. But then Google came along and adopted Kotlin for Android on low-powered machines with main thread UI issues, network APIs, and a less potent VM. And people started using Kotlin in single-page web apps, where the runtime, client-side, where the runtime takes care of threading, and APIs for I/O are asynchronous, and potentially at least on Node.js runtime on the server, which is the same sort of model. Those of us who grew up on a virtual machine, well, a grown-up virtual machine, and one thread per request have few concurrency problems that aren't delegated to Postgres, and we'd rather not have to maintain the distinction between suspend and not suspend functions. Now, many people disagree with us and love coroutines. They love structured concurrency and the flow and working out whose job it is to be catching cancellation exception. But even if they haven't divided Kotlin developers, and I think they have, coroutines have divided functions. The problem is that the type system treats suspend specially.
So Kotlin now has colorful functions. And Bob Nystrom coined the term colored functions in an article in which he was pointing out some of the ergonomic problems with async await functions in JavaScript. As a thought experiment, he said, imagine that a function is either red or blue. And a function that's red can call a red function, and a function that calls blue can call a blue function. And you have to say what kind of color you are calling when you call it. And a red function can call a blue function, but a blue function can't call a red function. If you designed a language like that, people would think you were crazy. But actually, that's exactly how async await works in Kotlin from an ergonomics perspective. Sorry, in JavaScript from an ergonomics perspective, and with suspend functions, we've sort of got the same thing in Kotlin. Luckily, we have the type system to help us there, but the types themselves are not a first-class concept. Initially, suspend wasn't something that you could express in, say, a type alias. Right? Now it is, but you can't be generic over suspend or not suspend. The actual implementation under the hood of a suspend function is not something that you can that is exposed to you and can be generified over. So we do have this difference. We've introduced, for the sake of concurrency, the sake of some of the platforms that Kotlin targets, we do now have a new ad-hoc rule going a bit against the grain initially, where Kotlin's type system was a lot more consistent to that of Java, and Kotlin had far fewer special cases and ad hoc rules. We now have introduced these ad hoc rules for functions.
So what effect, and that pun is only slightly intended, have coroutines had on the grain of Kotlin? Many will and do say that coroutines are now part of the grain of Kotlin. But the standard library is almost completely suspend-free, and there still isn't a non-blocking I/O API for files or sockets. Coroutines sort of allow us to express the difference between pure and impure functions, which can be useful for reasoning about our software. But even there, they're a leaky abstraction because they aren't typically using code that depends on time or changes mutable state. So our conclusion is that they've radically simplified the programming model for a large subset of Kotlin users, including almost all Android developers, and hardly affected the others at all.
Another language feature that arrived after 1.0 was contracts. So a long time ago, during the days of Kotlin beta, I wrote a testing library called Hamcrest. So Hamcrest allows you to compose matches and use those in assertions so that you can simplify the definition of new types of assertion. So in hamcrest, the assert that function checks the result, can fail your test if a match is wrong, can build the diagnostic messages that you want to come out of your test suite. And a matcher describes a particular match condition, can describe that condition, and can describe a mismatch if there is one. So I can write lots of different kinds of matches. Each matcher is really a factory function. It's a higher order function that returns a function. The matcher itself is a function that gets passed into assert that, called during the assertion, returns a match result. And then assert that does the work of actually being an assertion and generating diagnostics. The problem is that hamcrest cannot express at the type level some of the things that it's testing dynamically, unlike Kotlin.test since the invention of contracts. So here's a hamcrest test that is checking that a value is null or not null. If it's not, it's checking that it's asserting that it's not null. After that assertion, if the assertion passes, we're guaranteed that the text variable is not null. So I shouldn't need to use the null safety reference operator to use it. However, the type checker doesn't know that. Right? With Kotlin.test, the assert not null function has a contract within it that tells the compiler, if this function returns successfully, the parameter is not null. And therefore, after that assertion passes, I can use that value as if it was not null. And this is a real ergonomic benefit. So now I have tried to work out how to make hamcrest work with contracts, and I just think it's not possible. Right? There's too much function composition going on, too many higher order functions for the contracts to sort of trace through all the different types. Right? So I've started using Kotlin.test almost entirely, right? Just because of the ergonomic benefits. Which makes me a bit sad. I really like function composition, but I prefer the ergonomics of type safety. So this brings up an interesting aspect about grain, right? The grain of the language is caused by these different features of the language interacting. Right? As we add new features to the language, they interact in different ways. Right? If you look up feature interaction online, you see it's almost always a problem. There's lots of academic papers about the feature interaction problem in telephony and stuff. If you search for it, the Wikipedia page is actually called The Feature Interaction Problem. Right? And for people building telephony systems, maybe it is a problem. But for us programming language users and for programming language designers, features aren't making the system worse. Right? Every feature added to Kotlin makes the whole language better, adds capabilities to the language, adds convenience to the language. So it's not a problem that these things are interacting from the point of view of the language itself. But what is changing is our relative value that we are placing on particular language features. So when I wrote hamcrest before contracts, maybe I would judge different language features of Kotlin relatively like this. I like extension functions, I like instance methods, I like function composition more. We add contracts to the language, the entire language gets better, but that rising tide doesn't lift all boats equally. Right? Extension functions now are improved a lot, function composition not improved so much. Right? So now for my design decisions where I might have reached out and had a very compositional model, I will now maybe not take that decision and instead use contracts and extension functions for that design instead. So, features over time have been added to the language, have changed those design decisions, and new features are being added to the language right now. We've had a number of announcements in this conference. A number of big features have been announced in the past and are going through the process of becoming stable. And how is that going to change the way that the language features interact and the grain that we're going to be designing towards, and what are we going to do about that as our systems evolve as well?
So, context receivers. From the outset, Kotlin allowed us to write extension functions as methods. And in such a function, there were two receivers, there were two thises. And if we use scope functions like apply or run within extensions within methods, we could have more than two receivers. I don't know whether it was a deliberate thing, but certainly it was entrenched very early on in Kotlin. And we then gained the sort of Lambda with receiver type DSLs, such as the Kotlin X HTML. So that became part of the grain of Kotlin, supplying multiple receivers from our lexical scope. Now, work on Keep 87, the type class proposal we were talking about earlier, that was inspired by Scala, trying to get type classes, eventually morphed into these context receivers, which are still experimental, but more with the grain of Kotlin. I hate logging as an example for context receivers, but I'm going to do it anyway. We have an interface for Kotlin, interface for logging here. We can declare that a function or a method or a function type needs an interface in its context in order to run. Now, the types that are declared in the context are made available in the body of the function as a receiver. So the log in our read from somewhere here is the method in this context. How is context made available to the function? Well, if we have an implementation, something like this, then we can use the standard with scope function to supply it when we call write to somewhere. Now note, though, that unlike Keep 87, we have to provide the logging instance ourselves. The compiler isn't just going to go search for it. It effectively needs to be visible. And that's in keeping with the explicit aspect of the grain of Kotlin. Now, if we have two functions, both of which need logging in their context, we can put them both in the same scope. And as with withs, contexts are transferred from outer scopes, so that we can call both functions from a read and write function that itself requires a logging context. And we can define an arbitrary number of contexts for a function. So write to DB here says that it needs a data source and logging to do its job. And in these cases, the compiler will look out the lexical scope to try and resolve context for us. So here, it's providing the data source from my data source and the logging from whatever logging is provided to the calling function, this read write to DB. And we can create an object that implements more than one required context, and if we do, we can supply just that, and the compiler will do the right thing. Now, this type amalgamation may give those of you who are familiar with Java's checked exceptions sort of odd flashbacks, because the rules for context provision are basically the same as the rules for catching or propagating checked exceptions, and hold that thought. But also note that the way the compiler treats the types and contexts is a new feature. We weren't able to treat the number of types as a set anywhere else in the language, a number of types as a set. By that I mean that context logging and data source is the same as context of data source and logging. And this is a new facility, and just like contracts and coroutines for new facilities, it will take time for us to see how they can be combined with other features, and that combination will change the grain of the language. We said that Keep 87 begat context receivers, so how are they related? Well, if you remember our type class example, we wanted to be able to sort cats, but cats are incomparable. Well, context receivers give us a place to put conversions. So if we define our sorted as a context function that needs the context of a comparator, then we can call it with a comparator. And not only that, we can use contexts to supply other methods, in this case, an extension compared to. That means within a context block, we can write things like less than or equal to.
So contexts, unlike suspend, are a first-class concept in the language. What this means is we now can define our own colors for functions and treat them generically, treat them as first-class concepts, extend them ourselves. And it'll be very interesting to see how this changes the way that we define libraries, I think, especially libraries. Right? It's possible now that every library author is going to be defining their own contexts. And what happens when we try and combine these libraries? Will it be a massive clash and lots of adapters that we have to write? Or will we start converging on a few common sets of useful contexts that we all share? Only time will tell.
So, Arrow. The Keep 87 we referred to earlier was spearheaded by the then newly formed Arrow project. Spearheaded, get it? Anyway, Arrow was initially a way to allow Scala developers a way to use Kotlin without having to adapt to a language with a different grain. To do this, they needed type classes and higher kinded types and either an option and reader and writer and all sorts of other monads, as well as a way of abstracting over these monads. I think it's true to say that Arrow did some things that were against the grain of Kotlin to start with, like trying to tell us that we should be using option rather than nullable because, monads. But now context receivers give us things close enough to type classes to be acceptable to functional programmers, as well as being a good substitute for many monads. Reader and writer, for example, are being removed from Arrow. Arrow has, over the years, become better aligned with the grain of Kotlin at the same time as influencing it by helping define context receivers. There was still, though, the problem of the ironically named Arrow antipattern. That's this code, the one where the ever-increasing indent hides the flow of control. The one where if we had a cute notation, we could actually see what was going on. The one where most humans would rather have statements rather than expressions. And now the folks at Arrow have spent the last 5 or 6 years trying to find a way to get this working in Kotlin, and they've tried pretty much everything. They've tried making us write bind instead of on failure return it. They've tried clever use of destructuring, and they've tried compiler plugins. And actually, I have found it quite inspirational example in bending language features to find a way to achieve a goal. But they now have found a way to achieve that goal, to use context receivers to provide do notation without additional syntax. If this is widely adopted, I think it would change the grain of Kotlin again, moving us to explicit typed error handling, but with enough functional purity. Actually, we wonder whether control flow is a really important aspect of the grain of a language. Thinking it through, the grain of Java is sort of explicit control except for exceptions, but then checked exceptions made that bit explicit. The grain of Go, overly explicit errors and Go routines. Grain of Haskell is probably control flow with monads and do notation to make that a palatable thing. And maybe Lisp is everything can be solved with functions except control flow, so here are macros. So what's being talked about but not yet implemented? I made a list as Roman spoke this morning. So static extensions. So that allows us to effectively synthesize a companion object and static members. I think if we were to guess, I'm not sure that that would change the grain of the language completely, but these things are up for grabs. Collection literals. Again, I feel their use in DSLs, that would be interesting. So for those of us that want to be representing JSON-like things directly in our language, good. But maybe won't change the way that we program forever. Name-based destructuring, I think it's a great thing. It will cut down the number of things we break when we refactor, but probably won't change the grain of the language, and so on. Compiler plugins. Compiler plugins are an odd one, aren't they? Because it's possible to really just change the language completely with a compiler plugin, especially if you're prepared to write an IntelliJ plugin as well. So I think our bets are off there. After that, union types, I think those seem to be on the horizon, but then we have other things that might be missing from the language, structural types, higher-kinded types. The union type seems to be being discussed, the others not so much. And maybe Project Loom will further the division between client-side and server-side developers. All these things certainly would change the grain of the language.
So Kotlin's probably not been around long enough for us to be able to observe exactly how the grain was changed over time. Compared to, say, Java has changed over 25, 30 years, introducing things like beans, which had a massive effect on the way people wrote programs, introducing streams, another massive effect on the way people write programs. Still early days for Kotlin. It's interesting to see where it's going to go. Right? We can already see some of these unexpected forces nudging our code style in different directions. Right? And not always nudging them in the way that I like, but you might. Right? Personally, I'm not very happy that I'm getting nudged away from using compositional function composition and towards more imperative code by contracts. Right? But currently it's only in my test code, and so I'm kind of putting up with it, but maybe as contracts get better, I'll see that more and more in my production code, and that will make me a bit sad. Will I fight against it? Probably not, because I prefer the type safety, so who knows, right? The stuff that Arrow is doing is sort of, again, using statements, imperative style inside a pure functional context, and again, making it look a bit more imperative, but it's a good way of handling errors in a type-safe way. So again, I'll probably go along with it. Right? So yeah, I'll probably end up writing a little bit more imperative code and a little bit less compositional, but we'll see how it goes.
Will context receivers finally square the circle of functional error handling? What other ways will they be used combined with other features to form new grain?
But one thing I think we can be certain of is some of these features, context receivers, how they interact with coroutines, how contracts will evolve, they're going to have a significant change on the language, probably the biggest change coming since 1.0. And as a result, our design preferences are going to change. The grain is going to change. The benefits we're going to get from the way these features combine will change. And therefore, older parts of our long-lived systems are going to need to be brought up to date in order to take best advantage of the new grain of the language as it's changing. And continually refactoring our code, right, will be something that we just, well, luckily, we have IntelliJ there to help us, but I think it's going to be an important aspect as the language changes. We're continually evolving our systems as we work on them to take advantage of that grain. And in our teams, we'll be having these discussions about, well, what are the signals that we agree on that tell us that we are now going off grain and need to do that refactoring to bring our systems in line with the grain that we all now agree upon. So,
you can read more about the grain of Kotlin compared to Java in our book. I have a YouTube channel where I publish a new video every week, and I'm currently exploring how to use context receivers for transactions, enforcing segregation between pure and impure functions, trying to find workable rules of thumb for when we should use context receivers compared to extension functions or parameters or properties of a class.
So, thank you very much for listening. I'd like to thank my employer for sending me here. If you're interested in careers at Deutsche Bank, linked at the bottom there. QR codes will take you to those pages. And thank you very much. Please find us afterwards if you have any questions. Happy to talk more throughout the rest of the conference. Thank you very much. Yeah.